we didn't get through all the stuff we talked about last time. And so I want to finish that off. And our I'm happy to field questions if people have them. We spent last time talking about the rationale of how we would identify saturation profiles with depth, and also how we could do some calculations, what I always call back-of-the-envelope calculations, and the students laugh at that, to be able to calculate, for instance, flow rates of different fluids, either water flowing through the system, NAPL flowing through the system, or contaminant loadings being the product of water going through the system with the dissolved charge of the contaminant superimposed on that. And so it was all to be able to understand behaviors with multi-phase flow. So I just wanted to, maybe it's perhaps worth restating that in some way. And I don't want to belabor the point, but they are kind of important concepts. And so I will maybe try and make the case of what we're dealing with. By far, if you look in a practical sense at the, again, multi-phase flow, so in a practical sense, the very obvious key figures that we've talked about are the ones that must be by now emblazoned on your mind and hopefully represent some level of understanding of exactly what's going on. And so if we were to encapsulate these behaviors, you've seen these figures many times, and they are key pieces of our understanding of this. If we're looking at the static behavior, and if we're looking at the dynamic behavior or the flow behavior, then these are the ordinates of these figures. This is the saturation of water. This is the irreducible water or wetting saturation. This is the irreducible non-wetting saturation. And we know that these curves look like this as a drying curve, this as an imbibition curve, this is the bubbling pressure. Hopefully we'll use relatively standard terminology, and without messing around with all the subtleties of the relative permeability curves. This is between 0 and 1. This would be the relative permeability of the non-wetting, and this would be the relative permeability of the wetting. And so those are really the key concepts that underpin everything that we've talked about. How stuff gets into place initially and sticks there. There's this battle between gravity and interfacial forces. And if we then apply pressure gradients to it, or head gradients, how that stuff is then mobilized and removed at some rate. And so those are the key concepts. So if we're talking about, we talked last time about L-NAPLs and D-NAPLs. And so let's kind of rationalize exactly what's going on with L-NAPLs. Because what we'd like to do after today, 2.7 is actually multi-phase flow, but talking about the unsaturated zone, where the two phases that are present are going to be water, which is present in the pores, and gas, air, nitrogen, basically. And so in that, water is the wetting fluid, air is the non-wetting fluid. And so it behaves just the same as if we're talking about NAPLs, except now they have different densities rather than different characteristics. And so all of this revolves around the idea of, well, we've drawn this figure before, a ground surface, a water table below the ground surface, which might have a gradient attached to it, the vertical ordinate, doesn't matter whether z is upwards or downwards, and this would be the water table. This would be the vadose zone above it. This would be saturated below this. And so you recall that before we drew very deliberately these pressure versus depth curves, I guess. And if we did it for water, it would look like this. And if we went back up here as an extension of that, it would look the same. If we did it for air, it would basically be parallel to this line. Horrible, I could use a ruler on this, I guess. This would be air. And since we're talking about naples, if it's gasoline, for instance, we know that the density of gasoline is less than that of water. I wish I had some colored pens. And so this would be the L napple. I'll call it LN. Right? So all these just say is if you have a swimming pool filled with water and you submerge yourself in it, the pressure as you go down will increase more quickly if you're in water than it will if you're in gasoline or relative to just air. It'd be very imperceptible with air. This is almost parallel to this. We know that the difference between these two curves is what we call as capillary pressure. And so if we have a system which is just air and water. If we have air and water, then this is the air curve. Sorry, it's not, is it? This is the water curve. Capillary pressure, by definition, is equal to the difference between the pressure of the non-wetting fluid minus the wetting fluid. The non-wetting fluid would be air. The wetting fluid would be water. And so the wetting fluid here would be this negative amount. So this is the water table. Atmospheric pressure, we'll take that as zero pressure. So anything to the left is negative. Everything to the right is positive, plus VE, my terminology. And so this negative pressure for the non-wetting, small negative pressure minus a large negative pressure, is going to be a positive value of the capillary pressure at this part. So this would be the capillary pressure. It's going to be positive. And so all that means is it's going up from some zero value here, the difference between these two curves. And so if we draw the capillary pressure versus saturation curve for water and air, it's going to look like this. This is going to be zero saturation of water, 100% saturation of water. So you could think of this area here as being A, the air, and this being the water. So if you're at this elevation here, then you're 100% water until you get actually to the water table. This would be this. This would be the water table. Sorry. Not. This would be the top of the vadose zone, the tension saturated zone. And only after you get above this is part of the system airfield. Let's think of it that way. So this is air, water only. What happens now if you pour into this gasoline, a spill, if it comes from the surface? Well, what happens then is now the behavior is going to be changed slightly because we have this water table which responds to this vertical line here. But now we're adding on top of that a component which is gasoline, which sits on top of it, and that is going to actually not be able to coexist because it's also going to be buoyed by it. So what it will do is it will load it. And so some impression of that, I guess, we didn't spend much time on it. We really zipped through it. But this, remember we looked at this example last time. It's kind of looks like the saturation profile as you go down at depth. Choose a particular height here. This is the surface. This is a small saturation of the napple. This is deeper. This is about the same saturation of the napple. This is, if you look here, then the saturation of the napple is basically between this point and this point, so relatively a big number. which sits on top of the water table. And so physically what that would mean is, if you looked at this, well, this is the water that exists here. So the bottom curve here isolates water. This is the non-wetting component here. And this is the air, which is also, by the way, non-wetting. But what happens with this is, if you followed the same experiment as you dump stuff into the top and go from this to this to this to this, right? This tongue just physically moves down until it sits on top of the water table. What it does is it compresses the water table a bit so that now the pressures have changed. So if you were able to go into that section and be able to measure the pressure changes at different depths, this is the pristine case, which is A. By definition, the water table is where the pressure is atmospheric. Above it, the water is in tension, and below it, the water is in compression. So this is a positive compressive value, like air in your tires. This would be in tension because it's got capillary forces that you're pulling up the water in this capillary tube. If you add the water on the top, or gasoline on the top, this becomes the gasoline. So if you're measuring the pressures, if you like, in the liquid phase, this is all water. This is water plus gasoline. And as it continues at time 2, 3, and then 4, this is the final condition. So this is the water table. It's water essentially below here. And above this, because the height of this would be, this trajectory would be the unit weight of the gasoline. So in other words, what is it? We know that dP dz is equal to the density multiplied by g. And so then I suppose if we did this, then if this is 1, then this is rho g. Because this basically is pressure, this basically is elevation, which are the two components here. It's actually negative, right? So the slope of this curve is going to be given by the unit weight of gasoline. It should be different from water because they're different densities. But it's not really the point we're trying to make here. By definition, the point where this line intercepts the zero pressure, just by definition and convention, this is the water table. The point where this line intercepts the zero pressure mark, by convention, is what I guess we would call an oil table, top of the gasoline. And it physically identifies what's going on. And so in other words, if we go back to this, which was my plan, was now this is what the water table looks like and exists here. If we add on top of that water table, not something where for the liquid napple, the light napple, goes through zero, but it adds on just another water table, then physically what it would do is you could imagine that if this was the height to which the oil rose, this is water, then by definition this would be this intercept. And if we draw a line that's parallel to this steeper LN line, if I can do that, this would be basically what it would look like. And so now, as we go down through here, we have a pressure within the system. And if now we looked at the magnitudes of the difference between the pressure in the water, which is at this magnitude here, so this would be the capillary pressure, which is relatively high. And we draw now a diagram that represents, again, the air, and although it's non-wetting, it's less non-wetting than the air, and this is the Ln, I guess. This is water, this is now this. Then as we have larger magnitudes of capillary pressure here, which would be up here, it means that in the limit this would be that's not going to work out. Sorry. This has to be the capillary pressure increases. This has to be the napple in here, and this has to be the water that's here. And so this amount here, the difference between those, suggests that the saturation at this point has to be large saturation of the light napple that sits here. That's just supernatant, if you like, sitting on top of the water, as if it was water in a swimming pool, but actually now is also held in place by the gasoline. And so we'd expect as we go down through this that we'd have this region here, which is the oil table, increasing saturations with depth, because as we go up here, these are increasing capillary pressures as we go up here. And as you go down in here, the capillary pressure increases, the difference between the water pressure and otherwise. And as a result of that, we have larger saturations at the base of this, which is exactly what we'd expect to see. And so the other thing that we talked about last time was that if we have a water table here and an oil table here, the other consequence of this is that if we drive a borehole in this, which is this, is that we have separately an oil table that sits here, a water table that sits here, and these are within the aquifer itself, the formation. But if we put a borehole through here, no longer do we have kind of this capillary exclusion behavior, and we can do this little force balance that we did to be able to identify the fact that the depth, the thickness of product that you measure within the borehole is not the same as the thickness of product which exists within the aquifer. The amount in the aquifer is always less. So we can look at the saturation profile by doing what we did just 2 seconds ago on the previous drawing that I did, or we could just look at assuming that it's some uniform saturation. Really what we're doing is this, right? We're assuming that it exists at some saturation. The sum amount of water that exists all the way down as we go through here. This is the irreducible saturation of water. And above it, all the way up to the oil table, the napple exists, gasoline exists, somewhat all the way down to the water table which exists below it. And the calculation we did last time was merely to find out what the thickness was, this length W that exists here. And if we measure T within the borehole and know what that is, if we can calculate what W is, then we can subtract one from each other and we get the magnitude of this parameter T minus W. If we know what this height is, then we basically know that is this. And if we know what this height is and what its area is, then we can calculate the amount of stuff that's in there. Nothing more complicated than that. We know that a portion of it is air-filled, so this isn't going to be napple, but the rest may be napple-filled. And if we want to actually remove this green fluid, then we know that we can move most of it, but not all of it. And we know we can't get all of it out because, that's not what I want, because of this. Because we can't get into this irreducible non-wetting saturation as we come back here. So we can't get in here. So this is the amount of water that's always present. This is the amount of the non-wetting fluid that we would be able to get out. And so by definition, the final expression we came up with was that really the area that we can get out is going to be everything that's left that's green except for these cross-hatched areas. This is the irreducible saturation of the wetting phase. This is the irreducible saturation of the non-wetting phase, which is just going to be the smear, if you like, that's going to be left in there, and the remainder we would get out. And the expression for that is just this. And so we can think of it in terms of saturation with depth profiles, as we've kind of alluded to here, or we can think of it just as a plug of material, the green region that goes all the way to this axis here, minus, if we want to calculate how much we can remove, this region on the right-hand side, and either way. But they give us a quantitative way of being able to figure out what's going on. And so it's important to understand that, either in diagrams, as we have here, or otherwise. If we look at LNAPLs, then maybe that's a bit more straightforward, because we only have two phases that are present. Our problem in what we've dealt with here is that we essentially have three phases, right? We start off with air and water in this upper region, and then we dump in gasoline, and so we have three phases. For DNAPLs, it's much simpler. If we draw the same geometry as we had before, the ground surface, the water table, and I suppose a capillary barrier. Then we can do the same calculation. We have the pressure change with depth due to water. We have the pressure change with depth due to, I'll call it dN for DNAPL. We know that the difference between those is capillary pressure. We know that the NAPL pressure is going to be larger than the water pressure, and so this is always going to be positive. And if we drew our curve for this, so it's going to be this curve upside down. So let's see, I'm just going to flip it. This is PC0. This is increasing capillary pressure. And this is going to be the water part. This is the saturation of water. This is still 100% and 0%. So all I've done is I've taken this, well, this is no longer, I've taken this figure here, and I've flipped it, bless you, I flipped it around this axis, that's all. So don't know how to show that, I guess in the window. And so this is the DNAPL, and it kind of shows what you expect. If you go down in depth within here, this would be the water table, this is the ground surface, this is going to be the smear zone, and then there's going to be a lens of this stuff here, which is basically pure phase DNAPL. It's stopped by a capillary barrier because it can't get across that, because the capillary pressure isn't big enough. Even this capillary pressure isn't big enough to make it go across this barrier, and so it pools here at some saturation. And so if you kind of drew a line across here, I don't know if I can do it, all the way across all these diagrams, then it's basically saying that the saturation of the NAPL is large and the saturation of the water is relatively small and perhaps irreducible. And so that basically defines what's going on. So it matters whether it's lighter or denser than water in terms of what it does, because it changes how the capillary pressure changes with depth. Everything that we try and explain is absolutely explicable in terms of these capillary pressure diagrams, in terms of what we see. And if we look at an example of what we think, without worrying about all of these much more complicated derivations, etc., if we look at what the DNAPL should look like with depth, this is exactly the cartoon that we'd come up with. And it would be this. You drop it into the aquifer, it settles down to a capillary barrier. If the capillary barrier happens to be here, it will go all the way down to this. If the capillary barrier is here and your well bore only goes down part way, then it won't register the part that's below this. If your well bore is less than another well bore, then also again it will truncate it at whatever maximum depth it is, obviously. But if you look at the distribution of these as you go down, then this would be exactly what the DNAPL would look like. And so it's, well, you can see that this is basically a capillary pressure versus saturation curve. capillary pressures increasing as you go down in depth. This is the amount of DNAPL that goes in, that happens basically above the entry pressure. Until that point, there's really not very much DNAPL in there at all. There wouldn't be any if it hadn't already got in there. The remainder of this curve here is water. Or it could be partially air saturated if there's air entrained in here. And actually in this upper portion, the remaining portion that isn't either filled with the DNAPL saturation, this is the smear if you like, right? This is the smear because it's had a pressure larger than the entry pressure at some stages. It's been loaded from the top, and it's been able to leave a smear as it's gone down. And only below this magnitude here does this smear become something that's larger than the irreducible saturation of this DNAPL. And so that's what the distribution would be if we saw it. And physically what that looks like is, in the aquifer there'll be a puddle in the bottom of the aquifer which will have very high saturation of the DNAPL. Above that there'll be a smear and mainly water, and above the water table it'll be largely air, which again conforms to the capillary pressure versus saturation. And so it makes a difference as to how we sample it. And so in this case we don't have to worry as we did before, but if we think, I guess the other thing which is important to notice, say the capillary barrier was here. Actually, say the capillary barrier was here, and you drill a hole down to here. Well, of course it will fill up to here based on what falls out of the aquifer. If you now over-drill this hole, so now it's deeper, and it still has a capillary barrier, this would still be the limit to which the DNAPL had penetrated. But the mere fact that you have a borehole that goes down deeper is that the bucket will just fill up with more water, or more NAPL, because it can come out of the stuff that's already there. And so, because you have 10 meters versus 8 meters of this stuff, it doesn't mean that in the aquifer it would actually be 10 meters deep, for the reason that we stated. And so, in the same way that for something, free product that floats on the top is a bit of an anomaly, because the true thickness of that is not what you necessarily measure in the borehole, it is actually less than that. For DNAPLs, it's the opposite case. If you look at the borehole, it has to be actually at least as thick and maybe thicker than what's in the system. So if the capillary barrier was here, then this would fill up, so this would register a depth which is more than that. And so you have to be at least a little bit aware of that. What else? So that explains the behavior. It follows on directly from what we were talking about last time. The other behavior that's related to this, I think, is also, both of these figures are out of Feder. It makes the point about what you'd expect the distribution to look like if you had either a high porosity or a high permeability aquifer. Yeah, bad terminology actually. So high perm, actually, let's do this. I don't like that. I think it's actually referred that way in Feder's book. But so if you have high permeability, so high porosity doesn't necessarily mean high permeability, right? So you could have 30% porosity in something, but it could be tiny little pores, 30% of which were pore space, and 70% were solid, just like in a shale. Or you could have 30% in a gravel, where you have 30% are big open pores in the gravel, maybe ½ an inch in diameter, and the other 70% is the gravel, solid. So high porosity doesn't necessarily mean high permeability. There's not a correlation. But high permeability, from what we know about the Leverett function, capillary pressure, interfacial tension, permeability, over this. So we know from playing around with this that capillary pressure, entry pressure, is proportional to N over K square root. Just from looking at this. This is a number for the bubbling pressure. It's 0.3. And so at bubbling pressure, then this relationship has to hold. So a high permeability would mean a low capillary pressure. And so it would be really easy for DNAPL to get into the system at very low capillary pressures. And so since capillary pressure increases as you go down, if you have something with high permeability, it would be invaded at a very low capillary pressure, here rather than here. And so you'd expect that the saturation versus depth profile would look like this. Makes perfect sense. This is the amount of DNAPL that is invaded. This is the amount of water that's left there. As opposed to if you have a really tight system, which it can't really get into, then all of a sudden the amount of DNAPL in that system would be trivial. And the amount that would be water would be relatively large. And so all of this kind of logically follows on. I think it's not an easy topic to talk about, but it all logically follows on from these capillary pressure versus saturation curves. And it ultimately allows us to look at these cartoons that we've talked about, that we have a puddle of this sitting here. If you have other capillary barriers that exist here, that you have these little puddles that sit on top of these capillary barriers, and above these capillary barriers you have these chimneys. It fills this up, it cascades off the side, gets captured, cascades off this side, gets captured. Doesn't necessarily have from side to side. And then ultimately, the place that can go no further is this really big capillary barrier that sits on the bottom. And so the kind of behavior we have is due to multiple capillary barriers that exist. And really, if you understand what happens at one of these, which is really what we're talking about here, then you understand all the components. So not an easy topic, but one that's, I think, important to what we deal with. So that's the first part in multi-phase flow. Oops. The second part is the other figure that we haven't talked about so far, and that is if we want to know something about how to remove stuff, then we have to understand, and we spent a decent amount of time talking about that last time, but it follows in exactly the same way. If you understand this figure, then it's really only a matter of being able to substitute it into Darcy's law, which we could write in its simplest way as something like this: hydraulic conductivity and change in head with depth. I think that's the easiest way to write it, because you don't have to worry about the different pressure things. Relative permeabilities, which is what this graph is, an absolute hydraulic conductivity, and a gradient, which is driving flow. And so this is the expression that allows us to take this figure and do something useful with it. But the actual figure that I think really tells us more in a physical sense of what's going on is something that's on page 57 of these notes. I just went past it. Is this figure here. This is a key figure. And it says it all. Right? It basically says that if you have a fluid which is, so this is 100%, this is green, this is red, water is red. So if you're 100% green saturated, then you're at this point here. Actually, you're over here, right? This would be 100% green. That means the permeability to the system, if you put a straw in and you suck stuff across here, the only fluid you'll get out of here is the green fluid, because you're 100% saturated with green. There is no red fluid. If you move so that you've got some of the water that's present in the system, if you suck out of here and you're in this region on the left side of this dotted line, then the permeability to water is basically zero, and therefore the proportion of red fluid is going to be 0, and the proportion of green fluid that you get out is going to be 100%. So you won't be able to, so that's great. So in other words, if you're sitting in the bottom on this capillary barrier with this little puddle that you're sucking stuff out of, if you have a borehole that goes into this, then you're basically in this regime here, and you'll be sucking out the DNAPL out of here. Great. You'll be able to take it out. As you physically remove the DNAPL, what's going to replace this as this area shrinks, it's going to have to suck in water from around it, because it has to substitute the removed volume. As it substitutes more of the water, then all of a sudden you'll be on a curve where this is no longer zero permeability, it's finite. So now you'll suck out on the red stuff, maybe out of the total flow that comes out, maybe 5% will be water, and maybe 95% will be green, the DNAPL. And as you keep on removing this, you'll replace it more with water. So the water at some stage will become dominant. I guess in this case you get both fluids flowing. The dominant one is because of the cross-sectional area that's wetted, because there's more saturation of the green fluid, it will make more green fluid. In this case, cross-sectional area, the higher saturation is red fluid. Remember, we said that we could draw this diagram for relative permeabilities almost like this, just based on the saturations versus relative permeabilities. It's really just the cross-sectional area that's wetted based on this kind of argument here. If it's 50-50 saturated, roughly you'd be contributing 50-50 from each phase. If it's 95 red and 5% green, it would be in those proportions, the proportions you'd remove. Oops. And so at some stage, as you keep on removing fluid from this, you will have replaced all of this with water. The green stuff will no longer be connected from one side to the other. Once the green is not connected from one side to the other, then the red has to be 100% and the green has to be 0. And that means it's anywhere on the right-hand side of this. So it makes perfect sense. So understand what these things are in a physical way, because you have some pretty powerful tools already to be able to do some calculations that are useful, that an employer would pay for, basically, I guess, which is our objective in this class, right? So no one's shouting, so I'm presuming that you understand, but if you don't, then let me know, and I can never tell with very little response whether I'm belaboring a point or whether we're making the appropriate, spending the appropriate level of time. So this is the same kind of diagram for a lighter than water fluid. This, floating oil. This is the amount that sits on top of the water table. This is water. Above this you have the oil table that goes up to some place around here. The oil table would be at some location. And so if you look here, this would be the amount of gasoline. This would be the smear of gasoline in the chimney. This would be the air that's present within the chimney, and maybe water that's saturating at irreducible saturation above the vadose zone. And below the water table, it would be almost 100% water saturated, with some incursion of the NAPL, but that dies off because it can't physically push down because it's buoyant, and therefore can't get that far down. So we won't do this page and page of derivation. I guess the other thing that makes sense to note in a practical way is how you could also end up with smearing this stuff through the aquifer column. And that is if you have a water table which has the tension saturated zone or the capillary fringe sitting on top of it, and you spill stuff on it, then this will be our lens of gasoline that sits on top of here. It depresses the water table and compresses the tension saturated zone above it just by its self-weight. This is the smeared chimney that comes here, which is fine. It's happy to just sit here. This is the profile of saturations with depth on the right-hand side. If seasonally the water table drops, then all of a sudden there's nothing holding up this lens of gasoline. Lens of gasoline drops. It happens to smear all the way down as it goes down because it initially was present all the way out here, and you'll end up with this now laterally spread chimney. it rains again in the fall, and the water table rises, and it retreats back up here to its previous condition. So there's really no difference between this stage and this stage except for two things. One is that you've smeared this zone underneath, which didn't exist before. And secondly, because you're jiggling around with this stuff, instead of the lateral extent of this lens being over here, now it's gone a bit further and a little bit further just because it's being messed around, it's been moved up and down. And so it's a way that it can spread laterally and also be present below the groundwater table, even though it shouldn't really get there. But the mechanism it's got there is just by a rise and fall now. Yeah.
Would the lens thickness also decrease?
It has to, yeah, if it's constant volume. Yeah, good point. Yeah. Yep. And so we've talked about this, so I won't go through this. So those are the key issues. Again, you stand on a site. Did I close it? Maybe I did. So forget this. Yeah, so fine. So to be able to calculate where this is, we talked about well bores and what you do. Well, you need to be able to do two things, right? You need to be able to figure out where the water table is, or the oil table if it's a floating product, and the water table underneath it, or the water table if it's a sinking product, and where it goes into this lens. And so the easiest way to do that is just with a borehole and a water level indicator. So a water level indicator is just a piece of so it's a dual indicator. So it's basically a measuring tape which has a conductor, a wire conductor on one side, a wire conductor on the other side, which is sheathed, which is really what this is. They go down from a battery, they have a light in the circuit, and they go down into this little probe. The probe basically has one of the conductors going in here as a tip of a pencil, basically. Inside a casing, the other conductor's on the outer casing, and they have no connection. When it goes into water, all of a sudden you make the circuit, and the light goes on because you've made a circuit. And it is able to sense the difference in the resistance between air-water contact and the water-napple contact, and you can basically drop it down until the light goes on, take the reading at that depth, go down to the next interface, and you have those two identified. And so pretty straightforward technology, very, very simple. And I guess from what it said here, they cost a couple $100 each. And I don't know if they have any places where you're using it. I guess this guy might be using one, just dropping it down a borehole until it finds out, until the light comes on, take the reading off the collar of the well, and then you can translate that into an elevation somewhere within your aquifer. More sophisticated ways of doing it as well with paste. We'll talk about those maybe later when we talk about site investigation. So, all right. So the reason for, well, hopefully not belaboring this, but spending a decent amount of time talking about this is the idea that although we've talked about non-aqueous phase liquids in groundwater, the behavior for water and air in the system is exactly the same as water and DNAPL. One happens to be a wetting fluid, which is the water. One happens to be a non-wetting fluid, which is the air. And we can, everything that we've talked about so far in terms of capillary pressure versus saturation diagrams, and relative permeability versus saturation diagrams holds absolutely. They'd be exactly the same. And they relate to the behavior of these two phases, which happen now to be water and the non-wetting fluid, which in this case is not a liquid, but it is a gas, air. And the water and the gas is these two components. It's interesting, I guess, in the history of this is that these disciplines grew up totally differently. So actually probably three disciplines. So groundwater hydrology, agronomy, which is interested in the water that crops will get in the unsaturated zone, hydrology, which looks at putting wells down to be able to feed, clothe, and to water populations as water supply, and making sure that the water is clean. Contaminant hydrology, which really only developed in the last 40 years, since 1970 onwards. If you ask people what there was a problem with groundwater contamination in 1970, they said, what problem? And petroleum engineering, which is dealing with multi-phase fluids, which are petroleum reserves and gases. And so those three disciplines basically developed completely separately until maybe the 1940s, where you see Leverett curves, etc., trying to uniting these. But if you look at unsaturated flow, the discipline which it grew up with was agronomy. And so in agronomy, there are a couple of concepts that we should note. The first is this thing of matrix potential. Which is often given the Greek symbol psi, which is equal to the pressure of the wetting phase divided by the unit weight of the wetting phase. And this is kind of like our head, except that it's negative. It's in the tension zone. And so matrix potential is defined by this. It's in units of length, meters. And so that's one thing that we maybe should be aware of. I guess the other thing is that we also work in terms of volumetric moisture contents. And usually the symbol which is used for that is theta. It's a fraction. And volumetric moisture content is equal to the volume of water divided by the volume of the voids. So, in other words, that would be equal to, so how do we define that? So porosity is equal to the volume of the voids divided by the volume total. And so, what's the other one we want to calculate? The volume of water is equal to what? The volume of water would be equal to the, you've done this right, volume total times the porosity. This, by definition, is the volume of voids. I guess that comes from this. Yeah, that's just a rearrangement of this. And if you multiply this by the saturation of water, that would give you the total volume sum. So the volume of voids multiplied by the saturation is the volume of water. And so I guess we can rearrange this, is that saturation of water, just by taking this, is equal to the volume of water divided by the total volume times the porosity. Just rearranging this. And I suppose volume of water divided by total volume is the porosity. Doesn't make sense. What have I done wrong? Saturation of water is equal to the volume of water total. Oh yeah. Volume of total divided by the volume. What else do I need to do? Well, I guess I know that moisture content. I know the end result. Volumetric moisture content is equal to the product of porosity and saturation. Is that right? Yes. So how do I get to that from this? I'm not doing a very good job of this. This is volume of water. I guess I could multiply top and volume by voids. I guess that's right. And if I have that, I have volume of voids over volume total. So this term here would be porosity. and the volume of water, and this would be volumetric moisture content. So this says the saturation of water is equal, yeah, okay, so same thing. So I can actually derive things. So this is just manipulating this. So I guess this is the only important result. Is that, so when the volumetric moisture content is equal to the porosity, it means it's 100% saturated. So that if we drew capillary pressure curves versus saturation, then they would look like this. This would be capillary pressure. This would be saturation of water. They would look like this. This is no different from what we've done before. If we then plotted this against volumetric moisture content, then this upper limit here would be porosity, and this lower limit also would be 0. And the vertical axis would be, really this is, I guess this is actually the negative water pressure, but it's really the capillary pressure. And so this would be equal to matrix potential. So there's absolutely zero change. This, instead of being a irreducible saturation of water, this would be an irreducible moisture content of water, etc. So they just change it. So it's only due to the fact it's a quirk of history that they've grown up in different disciplines. And so our reasons for mentioning this is that, I don't want to talk about this. This is what we've defined here. We already covered this. And so we can define matrix potential as a pressure divided by a unit weight of the fluid phase. And as a result of this, I'll come back to this, we can now define behaviors in terms of capillary pressures and saturations switched into matrix potentials and volumetric moisture contents. And so one way to do this is something that we've already looked at slightly. It's a little complicated mathematically, but the reason for doing it is quite straightforward. And the reason for doing it is this. If you look at the capillary pressure versus saturation curves, or matrix potential versus volumetric moisture content curves, they look like these curves on the left, right? These are the entry pressures. These are how pressures change as a function, saturations change as a function of capillary pressures. We know from what we talked about before that this, because the capillary pressure, entry pressure is high relative to this, that this is probably a lower permeability, smaller pore sizes than this one, which would have more open pore sizes. We know from the shape of these curves that this one would be basically all the pore throats would be roughly the same size, because once we've invaded the first pore throat at this bubbling pressure, then it fills up all the other pores within the system. Whereas this one is the opposite of that. Once we've invaded it, we have to really increase the pressure to be able to start invading the rest of it. So we can immediately say something about the characteristics of the material based on what these capillary pressure versus saturation curves are. What we could do is, instead of plotting them on normal scales, as in a natural scale of saturation versus a natural scale of, this is actually pressure divided by unit weight. So this is actually matrix potential, but it's a linear scale, 50, 100, 150. We could plot these data on a log scale, both the saturation, in this case what we'll call an effective saturation, but basically the same idea, and an effective capillary pressure, a log pressure. And if we do that, we get these curves. So these curves are exactly equivalent to each other. They're exactly the same data. Data for curve number 1 are this one. Which one? Well, let's ask ourselves which would be. I guess we could figure out what the simplest one would be the one with the lowest entry pressure. This is number, I guess this is number 1. So the one with the lowest entry pressure would be this one. This is capillary pressure on the top. Small number, large number, much larger number. So the one with the smallest entry pressure is this, which would be this one, which therefore has to be this curve, which hopefully is number 1. This one is number 1. The one with the largest entry pressure is going to be number 4, which indeed it is. So those are the two discriminating factors of the magnitudes of the entry pressures as to where the 100% saturation curve crosses. The other feature of this is the slope of this. Here, this is a very flat curve. It means that as soon as we invade at this pressure, we invade everything. So on this curve, we'd expect that as soon as we invade, then as we increase the pressure, we don't have to increase this this pressure very much to be able to invade the rest of the system. So that would be signified, I guess, on here as basically a vertical line. So now, if you have a pressure where you get entry, if you increase the pressure a small amount to the right, all of a sudden you basically saturate the whole thing. And so the one that fits that would be the one with the steepest curve. So this one here with the steepest curve, most vertical curve, you'd think has to be number 2. And it's this one here. And the rationale is that as you invade this at the breakthrough, the bubbling pressure, all of a sudden a very small change in the bubbling pressure, by moving up a small amount here, you basically flood the whole thing. Here, you move over here, you flood the whole thing. And so we can say something about this. So I reiterate that these curves on the right-hand side are exactly the same data points as these, but they're just plotted on a log-log curve basis. And so in the same way that if you take an expression that says x and y, and if you have a curve which is represented by in that as this, then you know that the equation of that curve, I don't know, this is c, this is y equals mx plus c. The intercept, the gradient of this curve, which is just the slope of this. And so the convenience of this is if you take these data and you plot them in log-log space and they plot as straight lines, then you can take these curves and you can represent them by something that looks like this parameter is equal to a constant plus another parameter times its inclination, and that's it. And so that was the observation of Brooks and Corey, who are agronomists, who basically saw that you could take these relationships and you could define the volumetric moisture content, volumetric moisture content. So on our capillary pressure versus saturation curves. So on our capillary pressure versus saturation curves, that looks like this. So this is saturation of water, 100%, sorry, no. Sorry, let me redraw this. There's two curves. So what is this and what is this? If this is 0 to 1 and it's saturation of water, this is the irreducible wetting saturation. This is the irreducible non-wetting saturation. If we look at this in terms of volumetric moisture contents, then we know that this is 0. We know that this is porosity, right, from what we talked about before. If we define these other ones as this is the irreducible water saturation, the amount of water we can't get out is this. And if we define this one as the saturated moisture content, where it's got as much water in it as it can take, and it's got a bit of air still left in there. So this would be equivalent to the irreducible non-wetting saturation. The non-wetting phase in this case is air, right? And so this would be this term. So now what we're trying to do is define the behavior in terms of a particular volumetric moisture content that we find ourselves at, which would be this magnitude here, as a function of two material properties. One is the maximum amount of air we can get into the system and the amount of water that's left in there, which is this line here. And what it looks like when it's 100% as much saturated with water as we can get, which means this point that we can't get across here. And so the ordinate of this point here is a value of a volumetric moisture content and an actual pressure. And so the terms that we're going to be dealing with are this volumetric moisture content and this pressure. So those are the physical features in the field that might change. Pressures might go up and down, and moisture contents would go up and down. But for any particular material, the irreducible saturation to water and the ultimate saturation when it's fully saturated and the bubbling pressure are physical properties of the medium. So if I draw a square around this, this is the state of the porous medium in these squared terms, and all the other terms in this equation are physical properties of the medium. And so the rest is just manipulation. And so the postulate of Brooks-Corey was that you could write an equation that represents the capillary pressure curves like this. If you divide everything through by this saturation phi s, which is in the equation below, then you end up with this expression. If you manipulate it to get to this, you end up linking what's referred to an effective saturation to whatever pressure your aquifer is at, the bubbling pressure, and a gradient. And if you like to think of it as such, then I think you could think of basically, the explanation of this is to take the capillary pressure versus, I still write in saturations, a capillary pressure versus saturation curve that looks like this. And so the effective saturation is basically taking this curve and cutting it off at this point here. So that this is an effective saturation at the top, and it goes between 0 and it goes to 100%. But the 100% mark is at what was before not the 100% mark, right? This would have been 100%, this would have been 0. And so all it's doing is it's saying that the active range at which you're going to measure saturations, instead of being this full span which goes to 100% saturation, you're going to cut it off at this point here. And you're going to measure ordinates in that. So that's really what this expression is. And so what that allows you to do is to write this expression as this. And the final deal is that you have a very simple expression that represents these capillary pressure versus saturation curves. Saturation changes with capillary pressure according to the entry pressure and a slope of a line, and it's basically this curve here. I hesitate to do this because it's going to screw you up, but bear with me. This is the same curve we drew before, right? We said x, y equals mx plus c. In this case, this intercept is at this point here, which is the bubbling pressure. This is PB. And the slope of this curve, m, is just this term lambda. This term here. Slightly on its side. So that's just the rationale for it. So yeah, I didn't mean to take it off. So that's basically the idea. And so it may seem a little esoteric as to why we're doing this, but it's because we can use a very simple equation, the one that's boxed at the top here, to be able to define a curve. And a curve that can then be used for lots of things. And we know that, for instance, when lambda is very large, in other words, a curve that looks like this, right? To go one log cycle, lambda will be very large on this steep curve. So that means that the pore space in this porous medium will all have the same pore sizes. You invade one of them at this particular bubbling pressure, instantaneously it'll invade everything. If lambda is very small, so in other words, going across one log cycle, the height of lambda is very small, then it means the opposite. It means it gets entry into one part, can't go anywhere else. You have to buy a big change in the pressure that you apply to invade the next little pore space, then the next one, and the next one, only by increasing the pressure. And so it may seem kind of random for us to do this, but it's so that we can actually define curves that do this. And so an exposition of what we just said is exactly that. If you think about a curve where all the pore spaces are the same size, you get entry at bubbling pressure, immediately it floods the whole system at a very small change in pressure. If you have a system where the initial pore throat is larger, so you're higher up on this axis, it's along here, and as soon as you invade it, then all of a sudden you have to really jack the pressure up to get a big change in the saturation. This is the change in the saturation, delta S. This is a change in the pressure. So in other words, to get a big change in the saturation, you have to have a big change in the pressure that you apply to get there. So I think it's useful always to think about this in terms of physically what it means and how it translates from, albeit a diagram, to be able to do that. And so the effective parameters are effective saturation, which could also be an effective volumetric moisture content. They're equivalent to each other. An effective matrix potential, or a capillary pressure divided by unit weight of the fluid. So these are equivalent to each other. Before we talked about capillary pressures, here we're just dividing through by a normalizing parameter. Okay. So one reason to do this, and perhaps we don't have any time to spend on it, but is also that if we can use these universal ways of representing capillary pressure versus saturations, then we might be able to use this in a universal way to represent relative permeabilities and saturations as well. And one very useful method to do that are the so-called Van Genuchten curves. A Dutch scientist now working at UC Riverside, Irvine or Riverside, I can't remember which. And an empirical way of being able to, and this is covered quite well in Fetter's book, of being able to define these capillary pressure curves as a function of either volumetric moisture content and matrix potential, or saturation and matrix potential. You know, these look very similar to what we've seen before, but to be able to do it in terms of some empirical parameters. And so all it really is a way to be able to figure out exactly how saturation changes as a function of capillary pressure, and to relate that to a number of parameters that describe your system. One would be the irreducible saturation of water. One would be a parameter alpha, which appears here. One would be a parameter n, not porosity. which we've used in the past, and another parameter m. And so kind of looks complicated. It is complicated, but these equations are just the equations of these curves that satisfy the fact that they asymptote at some irreducible saturation and some maximum saturation, and they have this shape in between. So these are just curve fits that manage to do that. And so that seems that it's kind of complicated because we're just defining another curve. But the utility of this is that these parameters, alpha, n, and m, which are just scaling exponents, can actually be related to whether it's a clay or a sand or a silt or a gravel. And so there are tables of these. So there's two reasons that these Van Genuchten curves are useful. One is if you know what your material is by just dragging it out of the ground and you say, well, it's a clay, then you can say something immediately for that by determining each of these parameters. And if you know what these parameters are, immediately you can define the shape of this curve, which was something we said was not very easy to do before. So that's one reason for doing it. The second is that if you know these parameters, you can also immediately, from the sand, from the soil type, knowing what these parameters are, you can immediately be able to define your relative permeability versus saturation curves as well. And so in addition to the Van Genuchten method being able to give you a picture of a capillary pressure versus saturation curve and a method to be able to do that, it can also give you a picture of the relative permeability curve, how permeability varies either with saturation or with, well, volumetric moisture content, right? So this is just a proxy for saturation. Or since we know that if you look at our capillary pressure versus saturation curves, being capillary pressure versus saturation, since relative permeability is related to saturation, then presumably since saturation is also related to capillary pressure, then saturation must be related to capillary pressure, which is also related to head. So this term here might seem strange that you're relating the relative permeability to head rather than to volumetric moisture content. But the rationale is that permeability is related to volumetric moisture content or saturation. Since saturation is uniquely related to capillary pressure and capillary pressure is related to head, then we should be able to draw the equivalence between these. Relative permeabilities must also scale with heads. And so if you know what the hydraulic head is in with your aquifer, if you know the values of these parameters alpha, n, and m, which by the way you can get for different materials, which are just shown here, then immediately you can construct the relative perm curves that we think are so elusive to us in being able to determine the behavior of this, of Kr versus volumetric moisture content. So that's it. So the big picture is that we've divided things into static behavior in terms of capillary pressure versus saturation curves, and dynamic behavior in terms of relative permeability curves. We've talked ad nauseum about what those physically mean in terms of air and water saturated systems, L-NAPL and water saturated systems, and D-NAPL and water saturated systems. How we can use them to say what saturation looks like with depth within these systems. How we can use that information to also say something about if we try and remove fluids from it, how we can calculate what the rates at which we would remove fluids from it would be, and when we'd stop removing fluids when we get to these irreducible saturations at the edge. And also if we're just pumping water through it and dissolving some of the free product in that water, how long it would take for us to be able to completely deplete the system of that component. So we've actually covered a lot. I realize we're at the end of the fourth year. Might feel like the fourth year of the class, but we're at the end of the fourth week of the class, the 8th session. which isn't too far in the semester, but actually you have some pretty solid skills to be able to do some useful things in general and useful to an employer in particular as well, I think as well. So I'm going to leave it at that. I never leave much time for questions, but I'll take questions. I know you're always chomping at the bit to get to your next class or to go to the bars. It is Thursday, I realize.